Last week, we discussed the gold standard when it comes to identifying causal effects, random assignment. However, many of the questions that social scientists are interested in can't be answered with randomized controlled trials, whether for practical or ethical reasons. For example, let's look at the question, would more police make us safer?
All right, you scrawny beanpoles. Becoming a cop is not something that happens overnight. It takes one solid weekend of training to get that badge.
Forget about the badge! When do we get the freaking guns?
Hey, I told you, you don't get your gun until you tell me your name.
I've had it up to here with you, rules!
Women always have trouble with the wall. Can't ever seem to find a door. You missed the baby? You missed the blind man?
Just like in our previous example, we have a treatment variable, the number of police officers per capita, and an outcome variable, the violent crime rate. One difference between this question and our previous example of hospitalization is that hospitalization is a binary or discrete variable. Either someone's hospitalized or they're not. But police employment is a continuous variable. There are an infinite number of values it can take between 0, meaning that there are no police officers in a city, and 1, meaning that every person in the city is also a police officer. How can we start to examine the relationship between two continuous variables like this? A great place to start is usually with a scatter plot, which plots each of these data points in a two-dimensional space. Take this scatter plot of height and weight, for example. Each dot represents a person that we've weighed and measured. A dot's position on the horizontal axis represents a person's weight in pounds, and a dot's position on the vertical axis represents that person's height in inches. Looking at the scatter plot, we can see that people who are taller also tend to weigh more, creating this upward sloping shape to the scatter plot. We should then conclude that height and weight are positively correlated. Let's have a look at a different scatter plot. This time, each dot represents a US state in a given year. We have 20 years of data for all 50 states, so there are 1,000 data points in total. The x-axis represents the tax in cents that each state levied on a pack of cigarettes in a given year, and the y-axis represents per capita consumption of cigarettes in each state in each year. Compare the shape of this scatter plot to the previous one. This time, there's a downward sloping shape to the scatter plot. So we would conclude that cigarette taxes and tobacco consumption are negatively correlated. Okay, so we can kind of tell from looking at a scatter plot how two variables are associated with one another, but let's try and get more technical. Let's try and quantify how related two variables are. Our first tool for doing this is called covariance. For any two variables, x and y, we can calculate the covariance between them using this formula here. So for example, for this data here, we can calculate that the covariance between variable x and variable y is 20.29. What is this number telling us? Well, because it's greater than 0, we can say that x and y are positively correlated. What else can this number tell us, though? Is it a strong correlation or a weak one? Well, it turns out that just by looking at covariance, we can't tell, because covariance is a scale-dependent measure. What do we mean by that? Well, for an example, we've got this data set of people's heights in inches and their weights in pounds. When we find the covariance between each of them, we get a covariance of 114.2. Okay, now let's create two new variables equal to each person's weight in kilograms and height in meters. When we calculate the covariance between our metric measures of height and weight, we get a different covariance of 1.31. Just by changing the scale of our variables, we were able to make the covariance shrink, even though nothing about the underlying relationship between our variables changed. To confirm this, look at the scatter plots of our imperial and metric variables side by side. They look exactly the same. All that's different is the scale of the axes. But these two scatter plots end up having wildly different covariances. If we can make the covariance between two variables as large or as small as we wish just by changing the scale, then the size of the covariance can't really tell us anything. Okay, so we'll need something else to measure the association between variables, something that's not scale dependent. Well, it turns out that there is an alternative available to us, the correlation coefficient. To calculate the correlation coefficient between two variables, we take the covariance of these two variables and divide by the product of the two variables' standard deviations. Because the units in the numerator and denominator cancel out, the correlation is not scale dependent. Let's see this property of correlation in action using our height and weight data. When we calculate the correlation between height in inches and weight in pounds, we get a correlation of 0.92. If we instead find the correlation between height in meters and weight in kilograms, we get a correlation of 0.92. Changing the scale doesn't change the correlation. Because of this property, the value of the correlation is bounded between -1 and 1. A correlation of -1 indicates that two variables have a perfect negative correlation, and a correlation of 1 indicates perfect positive correlation. Finally, a correlation of 0 means that there's just no relationship between the two variables. This scatter plot depicts two variables with a correlation coefficient of 0. Now, we'll increase the correlation coefficient. Notice what happens to the scatter plot. When the correlation reaches 1, we see that the relationship between x and y can be exactly described by a linear function. However, this scatter plot also depicts a correlation of 1, even though the slope of the line is different. So we have covariance, which can tell us the direction of the relationship between x and y, and correlation, which can tell us the direction and strength of the relationship. But in future weeks, we'll discover a measure that can tell us the strength, direction, and size of the relationship. So this third measure should be different for these two lines here. In the meantime, though, let's use the tools we've discussed to answer our initial question. Would more police make us safer? Let's start out with a scatter plot. As we can see, the x-axis is the number of police officers per 10,000 people in a city, and the y-axis is the crime rate per 10,000 people. Looking at the shape of the scatter plot, do you think the correlation coefficient will be positive or negative? Because of the upward sloping shape of the scatter plot, the correlation between police employment and the crime rate will be positive. Does this mean that cutting back police employment would reduce crime? Well, don't start a hashtag yet. Remember, correlation is not causation. But let's go a little deeper on this. Why might the correlation between police employment and crime be different than the causal effect of police employment on crime? What's likely going on here is that there are two causal effects occurring at the same time. Police employment causally affects the crime rate, likely by deterring criminals, as economic theory would suggest. But at the same time, the crime rate causally affects police employment in the opposite direction. When crime rates go up, municipalities might respond by hiring more police officers. So, when we observe the correlation between these two variables, we're seeing the impact of both of these causal effects simultaneously, even though we're only interested in one of them. What's likely happening is that the second effect, the causal effect of crime on police employment, is masking the effect of the first. When two variables both causally affect one another like this, we call it simultaneity bias. Let's look at another question to see a different way that observational data can mask causal effects. Does spanking your kids affect their character as adults?
A photo that's become a huge talker on social media shows a man who's offering to spank misbehaving kids.
So I sat down to talk about spanking with full-time ass whooper and part-time member of Guy Fieri's pit crew, Dwayne Stamper.
Parents today are more worried about being their best friend than they are their parent. We got a lot of bratty-ass kids.
Why have you become a spokesperson of ass whoopings?
There's no book on raising children.
Well, actually, according to Amazon, there are over 60,000 books written on the topic by self-proclaimed parenting experts like Deborah Godfrey.
I run a business called Positive Parenting.
So I guess the first question is, spanking or no?
No, absolutely not.
Dwayne Stamper, he actually had a stand that said it, 3 ass whoopings.
Yeah, it's terrible. Kids need love and guidance.
A 1997 study in the Archives of Pediatric and Adolescent Medicine found that children who get spanked regularly are more likely over time to cheat or lie, to be disobedient, bully others, and have less remorse for what they do wrong. The study concludes by saying that when parents use corporal punishment to reduce antisocial behavior, the long-term effect tends to be the opposite. Unfortunately, the researchers were interpreting the correlation between corporal punishment and adult antisocial behavior as a causal effect. What could be going on here is that there's a third variable that causally affects both spanking and antisocial behavior as an adult. Even if there were no long-term causal effect of spanking, the presence of such a variable would create a correlation. Can you think of something that might cause someone to be spanked more as a child and get into more trouble as an adult? One potential culprit is childhood antisocial behavior. Children with innate antisocial tendencies are more likely to get spanked, as they're misbehaving more at home, and they're more likely to have bad behavior as adults. This is called omitted variable bias, or confounding. How can we identify causal effects in the presence of confounding variables? The solution is to condition on the omitted variable. For example, we could compare identical twins, one of whom is spanked by their parents, and the other of which isn't. Since we're confident that both children have the same innate antisocial tendencies, as they share genes and environments, we can conclude that any differences we observe in their adult behavior are due to the differences in their punishment as children. So, to summarize, we've learned about methods of evaluating the correlation between two variables: scatter plots, covariance, and the correlation coefficient. We've also learned about two biases that can create discrepancies between correlation and causation: simultaneity bias and omitted variable bias. Next time, we'll learn about one more tool, one that's even more powerful than covariance or correlation, and one that we can use to combat some of the biases in observational data and uncover true causal effects: ordinary least squares.